All right, and hello everybody and welcome. This is part 4 of my discussion about the weight of the piston robot, how I determine the weight of the piston robot. Knowing the weight is important for some of the calculations. We're in Keyshot right now, and of course I want you to know hello and welcome, and I'm glad you're here. Enjoy. I have a YouTube channel. I invite you to subscribe. I think you would enjoy it. I do have a website, and this discussion about the piston robot and the weight of the robot, this is the page on my website where I do that and where all the various things that are that you can download, that's where we'll put them for this topic. I do like to remind everybody that any physically real object has the potential to hurt somebody. And my advice is, if you have a physically real object and you are managing it, then my advice is that you should manage it in a manner that is legally allowed and reasonable and safe. And if you can't manage it in this way, then my advice is do not create it as a physically real item. And we'll now go on to this part 4 of our discussion about the weight of the robot. All right, and we're getting ready to say goodbye to Keyshot. Bye-bye. I like Keyshot, but I did want to show you one other thing, which is I do my drawings actually in SketchUp Pro. And so here is that first scene in SketchUp. I like SketchUp because it's simple, but it's kind of primitive looking, but who cares? It works. It's simple. It makes it easy to draw things. And SketchUp can export an FBX version, which is the 3D drawing exchange format. And so we'll look at what happens if we do that. We'll tell it to export an FBX of this drawing. So this is in Maya by Autodesk. And Autodesk is a very well-known and famous suite of programs. They're as good a quality as you can get. I found with Maya and the SketchUp drawings that you can tune it up a little bit. And it brings in the colors and the altered opacity. It shows the hand of the robot with clarity. And this is in Maya. And Maya is I think Maya is okay. And so I don't use it much because the learning curve for Maya is just so difficult that I don't use it much. But what I wanted you to see was you can bring these SketchUp drawing files into Maya, which is Autodesk, using the FBX import. And I'm going to take some of these and put them free for download, the FBX, on my website. So anybody that wants this can go download it and look at it themselves on their own 3D drawing program. So there, I guess, is what I'm saying. And now we'll go look at some stuff in SketchUp. All right, and so now we're in SketchUp. And here is the right foot of the robot. The right big toe, the right little toe, and the right heel. This is the inversion eversion plate. You can see that the foot section everts and inverts off of this shaft right here. And this is some of the parts and the cubic inches of the part. And what I did was, you can SketchUp shows you it's 0.2095 cubic inches. And so I made a texture file and had that print on it so that I don't get mixed up about all these parts. But what I wanted to demonstrate for you was, this is a 1/2 inch from here to here. And so here's the toe on the ground. You can see it's pretty much lined up on the toe. And the toe can flex up until it's up here by a 1/2 inch. So the toe has moved up a 1/2 inch. So if the robot is falling down and lands on its feet, and the only thing that absorbs the fall is the feet, which would be the toes, then the fall of the robot will be stopped over a distance of a 1/2 inch. And the question becomes, what does all that mean? And the answer is, if it falls 16 inches under the acceleration of gravity, it will be going at 9.2 feet per second at 16 inches. And so it's going to go from 9.2 feet per second to 0 feet per second over a distance of a 1/2 inch. All right, I'm back in KeyShot, and we're going to do some physics calculations. We're looking at this foot. And let's see where we are. So, wallabies. Now, I have to say, sometimes this is what I look like when I get caught up in all this math. It's technical, but let me show you the physics calculator for this. So this is a physics calculator and for force, but you can go back over here to the uniformly accelerated motion calculator, and we have to find out which one of these we want to use. There's a whole list of them. And so what we want to calculate is velocity and time, and I like to put it in numbers that Americans use. So our initial velocity is 0. The displacement is 16 inches. The acceleration is 32 feet per second. That's the acceleration of gravity. And we want to see what happens. And so the final velocity is 9.24 feet per second, and the time required for this to happen is 0.289 seconds. And we have another calculation we need to do, and we'll do that, and then we'll go back to the video. And we switch to this one. All right, so our initial velocity is 9.24 feet per second. The final velocity is 0. The displacement is a 1/2 inch. And we calculate it. And so what it tells us is the acceleration is negative 1,020 feet per second squared, and the time required to do that is 0.009 seconds. And we have one final calculation, and that is, if we want to put an acceleration of 1,020 feet per second squared onto an object, we need to know what is the force needed to do that, and that one comes from the F equals ma system. And you again, we'll go back to America here. So now remember, the robot has 2 feet, so it's 187 pounds divided by 2, which was about 93 pounds, and the acceleration was 1,020 feet per second squared. And we'll calculate. And it says that you need 2,950 pounds of force to have that effect. So that's how hard you have to push on 90 pounds to slow it down from 9.24 feet per second to 0 feet per second over a distance of a 1/2 inch. And the question becomes, well, what is the acceleration? And the acceleration is 30 g, or 1,000 feet per second per second. And of course you're going to say, so what does that mean? And the answer is, you don't know what that means if you don't know the weight of the robot. But we know the weight of the robot. It's 187 pounds, which means each foot has 90 pounds on it. So you're going to take 90 pounds of weight and put 30 Gs, or 1,000 feet per second of acceleration on that foot for 0.01 seconds. And since it's 90 pounds, you can calculate what is the force, because the force is the mass times the acceleration. And the amount of force that's put on the foot is 2,800 pounds, which is about 1,000 pounds per toe. And each of these shafts can withstand 1,500 pounds of pressure force on them. So each toe can withstand 3,000 pounds of force. So the three toes can withstand 9,000 pounds of force, and what you're putting on the entire foot is 2,000 pounds of force. So what that means is the robot can let go of the bar, drop 16 inches, and land flat-footed right on concrete, and nothing at all will happen. And this is what you can do if you know the weight of the robot. And so that's what I did. Now we'll look at another SketchUp drawing. And again, this is in SketchUp. And I said to myself, so how do you figure out how much this robot weighs if you don't have it, if you can't weigh it? But I realized you can take all of the parts of the robot, get their cubic inches. And so I started with just the toes and the heel. Okay? And the structure of the toe, all of the toes and the heel are all the same structure, other than this little plate is a little bigger. And so I just split it out into all of its parts, and I took each and every one of these parts, and I got the cubic inches of that part. And then I put it on there as a texture file. So I have the cubic inches of all of these parts. Oh, here it is, 0.03, and this is 0.0086, and this is 0.0036. So they're all there, and I put them on there as a texture file so I wouldn't get mixed up. And an interesting thing, now this robot wasn't originally designed by me to be a military robot that was put together with pieces of metal, 2205 alloy stainless steel. And I put it together as a series of pieces of metal that can be bolted together. Now you can see that this is tilted down into that. It's not supposed to be, but these things happen when you're working. It's not a big deal. But I put it together so it can be fabricated out of metal and then bolted together, because that, to me, is the right way to create something in these alloy steels. But the truth is, if you're going to print this as a plastic part, you can combine all these parts into one structure. And I think that's what this is. She has stamped her foot on the floor. And now when I saw that, I looked, and she is pointing at the clock, which means I'm out of time. So I'll stop, and we'll pick this up with our next lecture. I guess that would be part 5.